Okay, everyone, I'm going to try this new way of making a lecture. I'm using the document camera in the class. It's kind of eerie having nobody in class in front of me. But the thing I want to mention to you is that we've already discussed. So today I'm going to try and make a 5 or 10 minute video here of one other very common problem that high power lasers face. Now, what's the first problem that we discussed? The first problem we talked about was spatial bleaching. Remember that? Where the standing wave that forms inside the cavity. And why is there a standing wave? Well, because you need an integer number of half wavelengths, right? And right where the antinodes are, that's where the field is maximum, and there's no field at the nodes. So the medium is being used very inefficiently because there are nodes here, so these sections of the medium are not being used at all. Meanwhile, these sections of the medium are being used a lot, and so gain can saturate, and we will talk about that later. But right now the key point is that spatial bleaching is a problem in high power lasers, and we avoid that. By the way, this is the day that lecture had happened. And we avoid that by going to ring lasers, and we've discussed that before. But there is still another problem that one faces in high power lasers, and that is the problem of. So let me just write this, that we've already discussed spatial bleaching as a problem faced by high power lasers, and and so today we'll discuss another common problem, and it's called thermal lensing. Okay, so that's the topic for today. Now, what do I mean by high power lasers? I mean, you need to recall, so I'm just going to say, high power lasers. So anything that is, several tens of watts, okay, output is high power. Why? Because remember that inside the cavity, the power can be 100 times higher. Remember, because it's only about 1% that you leak out. So it can be 100 times higher, and so all those elements that you put inside the cavity, okay, like you may have, the intra-cavity elements. And what are those? Like the gain medium, right? It could be a dye jet. It could be a solid crystal, whatever. So there's the gain medium, then there might be a Faraday rotator, there might be a half-wave plate from what we were discussing with ring lasers, remember those? So all these are facing this extremely high power. So, it's important that, how we manage things that go on inside the cavity of the laser. Well, thermal lensing is something that is a problem. And what is thermal lensing? Well, as you would imagine, so let's talk about thermal lensing. Well, so here's your cavity, right, the mirror, and inside you have, let's say, a gain medium, right, and let me just indicate it like this. So, well, there might be other components, but you have this gain medium, and it gets really hot, right? So the gain medium becomes really hot. And what happens when it becomes really hot? Well, for example, if the beam that's coming out of this laser, let's say it looks like, if the beam coming out looks like, it's bright in the center, and then it sort of is lighter outside, like a Gaussian beam. Well, then what may happen is that the gain gets really hot in the middle, but less hot on the outside. So as you look at because this beam is so hot, bright and intense in the middle, and then it gets less dense, less intense as you go outside. So you might have, as you move in the transverse direction here, okay, so let's say if you're moving in the transverse direction rho, okay, so your refractive index, gain medium, becomes really hot, which implies that the refractive index of the medium varies with temperature. Okay, so here's the problem, that it's really hot, and as the temperature is changing, the refractive index of the medium, which changes with temperature, and can acquire a radial variation. Okay, meaning that the refractive index can either decrease as you move off in the radial direction or increase. Either of those can happen. Okay, so the refractive index, if I wish to draw that here, and as a function of rho, with rho, then you can have either that the refractive index falls off like that, or you can also have that it's high here and low in the middle. Okay, so this would be a case where n of rho is least in center, okay, increasing outward, and this would be a situation where the refractive index is maximum at center, decreasing outward. So now, but why is that a problem? Well, this is a problem because you'll recall that the gain medium, and so let me just say this here, that y is the refractive index variation with temperature a problem. And by the way, why is the refractive index exhibiting this variation? Well, because the intensity of the laser, I should probably plot that too. Intensity it's a Gaussian beam, right? So the intensity as a function of rho, okay, so this is the laser intensity as a function of rho. Well, it's a Gaussian, right? And so because of this variation of the intensity, it's more intense here, therefore hotter here, right? And that can cause either the refractive index to be maximum or minimum. It can go either way. And then the refractive index changes as the temperature changes because you're less intense and therefore less hot on the sides. Okay, so that's why the refractive index is changing. So but why is the refractive index variation with temperature a problem? Well, because you recall that the intracavity elements, such as the gain medium and the Faraday rotator, for example, and the wave plate are all relying on Brewster's angle. Remember that? For minimum insertion loss. Remember that? Because you remember that we cut the, if you remember, we actually, so some real-time editing here, we cut the crystal, remember that? We cut the crystal at Brewster's angle, right? So it was something like this, and this, remember? So this is cut at Brewster's angle. Okay, well, but Brewster's angle obviously, relies upon, the Brewster's condition is that you get no loss for the p-polarized beam when this at this angle, that this theta sub b, and what is this theta sub b? It's this angle, right? The angle that the light that's bouncing back and forth, which is in the horizontal direction, makes with the normal to the surface, theta b, and this is equal to, so if you cut this at the Brewster's angle, then your p-polarized losses are minimum, and this angle is determined by, and here's the problem, by the refractive index, right? So it's the refractive index of the element, and my phone is, and then divided by the refractive index of the air. Okay, so here's the problem. So the problem is that the refractive index of the element, this is the intracavity element, and the refractive index of the element is changing with temperature. Which implies that the Brewster's condition is impossible to satisfy. Okay, which implies that you have losses. Therefore, if the Brewster's condition is impossible to satisfy, then which implies there are now losses, reflection losses, even for the depolarized light. So this is a problem. Okay, so this actually leads to thermal lensing, but the question is that, why do you call it thermal lensing? So this leads to thermal lensing. The question is, of course, that, why is it called lensing? Lensing implies, why is it called so? Because lensing implies that there is either a focusing or a defocusing of the light, and that, of course, is impossible to see from what we just did here. So why is it called so? And, of course, how to get rid of this. So that will be, I will take that up in my next video. Okay? All right, I'm going to end this one here and see how big the darn file is, and then we'll get back to discussing again. All right, toodaloo.